We'll again just look at a recap of what we went over last session. So let's look at this slide here, because this chapter on one population test focuses on performing hypothesis tests involving the mean and the proportion. And down at the bottom here are a couple of slides that you can use as a guide in terms of setting up the hypotheses, all right? Whether you are testing the population mean or testing the population proportion, you will note that the setup is fairly the same, meaning you'll have the null hypothesis and the alternate hypothesis, and then you have what is known as a decision rule. All right, so a decision rule is a condition or a statement that you evaluate. And if that statement that you evaluate is true, then the conclusion would be to reject the null hypothesis. So what you're seeing here, the decision rules that you see in these two slides, the decision rules compare what we call as a computed statistic. So we compare what is known as a computed value or computed statistic, and we compare that against what we call as a critical statistic or critical value. So the numbers that you see over here, here, they are computed based on, whether you're doing a t test or a z test. So these are the formulas that are used to compute what is known as a computed statistic. And as we learned last time, a computed statistic is based on, the sample or a sample. So the sample will be the basis for making a decision regarding the null hypothesis, whether we will reject it or we will fail to reject the null hypothesis. So on the other side are these numbers here that you see. These are what we call as the critical statistics. All right, and critical statistics are based on alpha, which we defined as, so this is alpha, which we defined as the significance level of a test. All right. Now, when we look at a couple more problems this afternoon, we are going to use another decision rule. And this decision rule will say reject the null hypothesis if. So the condition is we will compare what is known as a p-value if the p-value is less than the significance level. Okay. Now this is probably an important decision rule to remember, because when you use the p-value as a decision rule, all you have to remember is that you will reject the null hypothesis if the p-value is less than alpha. Unlike when you are using the computed statistic, comparing it to the critical statistic, you have to, the direction of the test, tells you whether the critical statistic is to the left of the distribution or to the right of the distribution. But when you're using the p-value, you don't have to worry about that. Okay? Now, what's the difference between, this decision rule and this decision rule. Recall that when we started talking about the critical value, right? That in this example that we did last time, we obtained the critical value for a right-tailed test where the significance level is stated as 0.05. So 1.645 here, we call this the critical value. And to that, we compare the computed value. So what is a computed value and a critical value? Well, a computed value or a critical value are points along or on the horizontal axis, okay? Such that here the critical value of 1.645 is that point there, and the computed value is that point over here. So what is a p-value and alpha then? What are they? Well, if you note here, alpha of 0.05 is an area, right? In fact, it's the area of the rejection region. So if we were to use this decision rule, and since we know alpha is an area, then the p-value must also be an area. Okay, so we're comparing apples and apples and oranges and oranges, right? So the question is, what area does the p-value represent? What area in the distribution? Okay, so let me make this a little bit bigger. All right. So the p-value that we obtained in this earlier exercise, here's the p-value we obtained, right? Let me rewrite that, 0.02275. Now this, we say, is an area with respect to the computed z, or computed statistic. In fact, this 0.02275 is the area to the right. All right, why right? Well, because this is a right-tailed test. So this must be 0.02275. So when the relationship between the p-value and alpha is this, meaning if the p-value is less than the significance level, that tells us that the computed statistic is inside the reject HO region. Okay? In other words, or on the other hand, if the computed statistic is not greater than the critical statistic, say for example, you generated another sample, and that sample obtained a computed statistic of 1.75. All right, the p-value associated with 1.75 will be a number that is going to be larger than 0.05. So that means that the 1.75 is inside the fail to reject HO region. Okay? All right, so I think let's now look at a problem where we are asked to use the p-value also as a decision rule. Okay, so let's look at exercise 1032, and we will solve this problem using the template as well. Oh, we'll solve it using the formula first and then the template. So using the formula, we're going to compute the p-value sort of by hand, and then we will verify that using the template. All right. Starting with a typical question that we ask for every problem. What is the variable of interest? Okay. But before we answer that, let's read the problem. It says, Dole Pineapple is concerned that the 16-ounce can of sliced pineapple is being overfilled. Okay, that's one keyword there, overfilled. Assume the standard deviation of the process is 0.03. Okay, so we know it is a standard deviation of the process. Therefore, this 0.03 is our population standard deviation. The quality control department took a random sample of 50 cans, so that's N of 50, and found that the arithmetic mean, X bar, was 16.05 ounces. At the 5% significance level, so alpha is 0.05, here's the question. Can we conclude that the mean weight is greater than 16 ounces? So this statement here translates into this, mu greater than 16 ounces, which is the interpretation of this. Okay, being the cans are being overfilled. So let's go back to X, defining what X is. Here we're talking about the amount of pineapple in a 16-ounce can. All right, and this variable is continuous. Next question, what is the population parameter being tested? We're testing the mean fill of the canning process. All right, so we're testing for mu. How do we set up the hypothesis? Well, we set up the hypothesis based on the given information or the keywords that we converted into a hypothesis statement. So we will say that H1 is mu greater than 16, H sub 0, mu is less than or equal to 16. The translation of H1 is that the canning process is overfilling cans. All right. This one says the canning process is not overfilling. So that's how we set up the hypothesis for this problem. In terms of the appropriate test statistic for carrying out the test, we know that sigma is given, right? Over here, since sigma is given, then the appropriate test statistic is using the Z distribution. So representing this variable X in this normal distribution, the mean is 16. The standard deviation of the population is 0.03. And X bar, they've determined X bar to be 16.05, which is somewhere over here. Okay. So we convert 16.05 into a Z value using the formula Z is equal to 16.05 minus 16 divided by 0.03 divided by the square root of 50. So the z value is equal to, I'm just going to ask Excel to compute this for me, 16.05 minus 16 divided by 0.03 divided by the square root of 50. Okay, so if you compute your z value, it is 11.8. Okay, so can somebody confirm my computation of z, please? I think that's correct. So where is 11.8 with respect to, let me move this over here. Oops. Where is 11.8 with respect to the critical z?
Your 11.8 is correct, by the way.
Okay, thank you. So how did we obtain critical z from previous problems? We used the norm.s.in function, right? 0.95. Why 95? Well, because the significance level of the right side of the tail over here, let me draw, let me finish this then, 0.95. All right, so this is the critical value. So the critical value is in this distribution is maybe over here. Okay, 1.645. Now my distribution is not drawn to scale, so don't look at the size of the area of the critical the area of rejection as proportionate to the size of the distribution. So if we compared the computed statistic to the critical statistic, the computed statistic is greater than the critical statistic. So by this decision rule, we will conclude to reject HO. All right. So the problem also asks us to compute the p-value, meaning what is the area below, above a z-score of 11.8. Okay, so this is the definition of a p-value. What is the area beyond a z-score of 11.8? We know that, if we use the empirical rule, right, that as z-score gets bigger and bigger and bigger, the tail end area gets smaller and smaller and smaller. In fact, for a z-score 3 and above, the area beyond 3 and above is going to be a number that is about 0.15 or 0.015. Okay, so imagine a z-score that is much larger than 3, 11.8. That means that the area beyond this 11.8 z-score will be a number that is very small, perhaps very close to 0. Okay, so let's see what that is. And I am going to use this time the norm.dist function. Oops, norm.s.dist function. All right. And the z-score, 11.8. And comma, the cumulative means it'll give us an area from 11.8 to the left. All right, that is what the cumulative parameter of this function says. It's really not 1. Let me make this bigger. Oops. Let's see. It's really not 1, but it is. Let's see if I can make this even bigger. Let me try a different function. Norms dist. It's still 1. But this one is the area to the left of 11.8. So the area to the right of 11.8 must be 1 minus this. And this is going to be a 0. It's really not going to be a 0 number, but a very small number. Let's make this bigger and see if it shows up. Okay. Well, looks like let me just see if my function here is correct. All right. Indeed, it is correct. Okay. So it's just making me nervous because you know it's 1 here, but I think there's going to be a lot of zeros. That's why it's rounding up to 1, whereas this is rounding up to almost 0.
I think there's about 32 zeros.
32 zeros, Doug?
Just about, if I did it right on my TI-84.
Okay, yeah, we will confirm that in the template, or maybe not, because I think template will round it to the 0. So anyway, let's see if I convert this into. Oh yeah, look at that. All right. So is this what you're getting, Doug? 1, 2, 3, 4.98 with like what, 32 zeros in front of it?
I'm not sure if I did it right because I haven't used this for a while, but I think it's 2.009 to the negative 32.
Oh, to the negative 32. Okay. Oh, there should be 30. 31.
It's way out
zeros. There. Yeah, it's going to be a very small number. Okay. So let's rerun this same problem, and then I'll go back to the to the interpretation of this p-value. All right, because that is important for us to understand. So let's use the template. Hypothesis testing for one population, and we use the z-test. So we'll select that. Hypothesized mean was 16. Direction of test, it's a right-tailed test, so 2. Sample mean was 16.0. What was that? 16.05. And the standard deviation was 0.03, is that right? Sample size of 50. All right. Significance level 0.5. So here we go. Here's the critical value. There's the output. Okay. So we obtained the same computed value. And the p-value is almost 0. And in this distribution that you see over here, you don't even see 16 because 16 is all the way, or 11 because 11 is all the way out over here. So the area beyond that is, we'll say, almost 0. All right. So are we clear in terms of how to obtain the p-value? You know, if you're using the template, you don't have to use the Excel function because the template will give you the p-value. You'll just have to know how to interpret that number, you know, meaning what does a p-value, a very small p-value, represent? Okay.
Hey, Renee.
Yes.
Could you quickly go over the z with the z value? Because I'm having a hard time. So I know if you use the template, you'll get that 11.8. But I'm curious about how to go about doing that with the TI-84.
Oh,
so,
I don't know. I do not use a TI-84. I'm sorry.
Okay. Oh, that's
so
fine.
you probably just have to use that. You know, maybe you may want to refer to your manual.
Okay.
You know, so you would just want to compute that using this formula over here.
Well, because I did type in the formula and like I typed in 16.05 minus 16 because that's, you know, the mean, and then you divide all that. But I get a very small number.
All
so
right. Yeah, here's what I have to caution you about when you are transforming a equation like this. Be very careful when you have to use parentheses so that you can preserve the order of operation. You know, whether you're using Excel to compute that for you or using TI calculator, you have to be mindful of you know, using parentheses, right?
that's probably what I forgot then. Yeah, the parentheses.
Yep. So that's a, you know, that's an easy mistake to make, and it can drive you crazy. So make sure that, you know, when you have equations like this, put parentheses, something like this, so that you know when you transfer it, when you transfer this number into your calculator, that you use the appropriate parentheses.
All right, awesome. Thank you. Appreciate it.
You're welcome, James. All right, so going back here, what is the interpretation of the p-value? What does that mean? Okay, now look at in this concepts. Here's the important slide that talks about the interpretation of the p-value. So what does it mean when you have a p-value that is very small, maybe as small as 0.001? Okay, remember that the p-value that we obtained, oops, why is this reflecting it on? So in the problem, okay, let me copy this. Okay. What does it mean when your p-value is quite small? So in that problem, our p-value was almost 0. Right? What this means is that in terms of the evidence that you have, which was the sample, which was the basis for computing X bar, which is used to estimate an unknown population value, that this tells us that you have a very strong evidence in rejecting the null hypothesis. So once again, the p-value is a measure of the strength of evidence that you have in rejecting the null hypothesis. So as your p-value gets a little bit bigger, you know, from 0.001 to 0.01 to 0.05, look at the description of the evidence. 0.05 is considered strong, 0.1 is considered as some evidence. Obviously, when we present evidence, especially when we are performing a hypothesis test between, say this, that we want as strong an evidence as we can. Okay? So recall that when we started talking about hypothesis testing, that the second step was determining the value of alpha, right? And I said that, typically alpha will range from 0.1, kind of like this, from 0.1 all the way up to maybe as small as 0.01, or even sometimes even smaller than 0.01. So that begs the question, what is a good level of alpha? Is 0.1 a good level of alpha, or 0.01 a good level of alpha? Now, the answer to this question is really dependent on, and this is now where we will introduce the type 1 and type 2 errors. All right, so let's look at the type 1 and type 2 errors, what they are. The alpha, let me type this up so that it's easier, you can read. Let me move this. So alpha is defined as the probability of rejecting a true null hypothesis, right? This is also known as a type 1 error. Okay, so in hypothesis testing, or even in any kind of decision making, obviously you don't want to make a decision, an error in your decision. Beta, the other error, which we will call the beta, is defined as the probability of failing to reject a false null hypothesis. This is known as the type 2 error. The thing to remember about alpha and beta is this. Obviously, you would want to avoid making a type 1 error, as well as avoid making a type 2 error. But the thing is that for a given sample size, when you try to reduce alpha, what that does is it increases beta, all right, or vice versa. If you try to minimize or reduce beta, that will cause an increase in your alpha. So basically what I'm saying is that there is a trade-off between alpha and beta. So when we go back to when I asked earlier, what is a good alpha? Well, the answer to that question is it depends. It depends on what? Well, it really depends on the cost. So we will, the level. So if the question was, which one should we minimize, knowing that there is a trade-off between alpha and beta? The answer to this question is this. It depends on the cost associated with each of these types of error. Such that whichever is costlier, minimize that error. Okay, so let me give you an example where we'll try to decide whether we can afford to increase alpha, therefore decrease beta, or decrease alpha, therefore increase beta. All right. So, you see a matrix here where you have the actual condition, which is unknown at this point, is that the actual condition could be that the null hypothesis is true, or that the alternate hypothesis is true, right? So you take a sample, n, over here, and based on this sample, you make a conclusion regarding the null hypothesis. So one conclusion would be to reject the null hypothesis, right? The other conclusion could be to fail to reject the null hypothesis. So since we are making our conclusion about a population parameter based on a sample, that there is always a probability or possibility of making either this kind of error or this kind of error. All right, so let's look at this matrix. What is the type 1 error? The type 1 error says the probability of rejecting a true null hypothesis. So here's the true null hypothesis over here. If you said you reject based on your sample, you concluded to reject the null hypothesis when in fact the null hypothesis is true, then this is what we call as the type 1 error, okay? Again, type 1 error is defined as the probability of rejecting a true null hypothesis. So if based on your sample, you rejected HO when in fact HO is true, then we say that you just committed a type 1 error, or this is alpha. The other error, beta, is defined as the probability of failing to reject a false null hypothesis. So that happens when you conclude to fail to reject when H1, let's just say, when H1 is actually true. Okay, so this one is a type 2 error, which is beta error. Now this is what we want to avoid, this kind of error. We also want to avoid this kind of error. What we want is to reject the null hypothesis when really the alternate hypothesis is true. So this one says this is a correct decision, okay? Or you would want to fail to reject HO when HO is actually true. So this one is a correct decision. So we want this as well as that. Okay, we want to avoid, or not, we can't avoid, but minimize either the type 1 error or the type 2 error. And knowing that when we try to reduce one, the other goes up. All right? So let's look at an example where we can apply the type 1 and type 2 errors. Let's use our criminal justice system as an example. All right, in the criminal justice system, when somebody is taken to court, what is the null hypothesis?
That they're not guilty.
Okay, so yeah, innocent, right? Person that is accused is presumed innocent unless evidence is presented to support that, you know, the HO can be rejected. H1 is this. Now let's translate these two in terms of the alpha. So for the criminal system, how do we translate a type 1 error? Okay, use terms that are non-statistical, not in statistical jargon. So type 1, we'll define this as, can you see the text? Is that big enough? Okay. So this is the probability of convicting an innocent person, right? Because type 1 is the probability of rejecting a true null hypothesis. So essentially, a type 1 error is when the jury returns a verdict of guilty on a person who is actually innocent. Does that make sense? How about type 2? Well, the type 2 is defined as the probability of setting a guilty person free. That is, this is the probability of failing to reject a false null hypothesis. So essentially, we're saying that the person accused is innocent when in reality that person is guilty. So which of these two errors do you think is costlier? At least from the way that our justice system works. Would we rather convict an innocent person or
Would it be
set
type
a
1?
guilty person free?
Would it be a type 1 error?
Meaning we want to minimize the type 1 error?
Yes.
That's right. Because what is the cost associated with the type 1 error?
Well, in this case, it'd be you're proving them guilty when they're actually innocent.
Yeah, so what is the cost associated with that? Convicting an innocent person.
Legal fees, restitution, the cost of housing them in a prison, etc.
Well, more than that. It's more than just monetary terms. Isn't it life and liberty? Right? Both of these we put so much value on. Now, if you guys still remember the OJ example, the OJ case, remember that? I mean, many of you probably were not born then. What was the outcome of the case tried in the criminal court? You guys remember?
He was found not guilty, right?
Okay, yeah. In the criminal system, the verdict was not guilty. But the same case taken to a civil court, what was the verdict? Same case. What was the outcome?
Guilty.
Guilty. So why the same case, why different outcomes?
Did they weigh the costs differently?
The what was that?
Did they weigh their costs differently?
They weighed the cost differently. Okay. What do you mean by that, Shoshana? What is the cost associated with a criminal in a criminal court, or I mean the civil court? The type 1 in the civil court is what? When an innocent person is convicted, what is the cost associated? Right. That person bears.
That they're in jail when they're not supposed to be.
Jail, is it jail time? And civil courts are typically, they're like a monetary, that the person accused pays money. So the cost associated with a type 1 error is monetary terms only. Okay? So in the type 1 error, in the criminal justice system, the alpha is as small as possible. Meaning we are not willing to, or as willing to commit a type 1 error in the criminal system because the cost is quite high. So in this case, maybe you can set your alpha at maybe 0.001. But in civil cases, you can afford to increase alpha, because when you increase alpha, what that does is it makes your type 2 error smaller. All right? So are we clear on that concept of the alpha and the beta as it relates to the question, what is a good alpha? You know, should you set your alpha at very low number, or should you set it at a higher number? And the answer to that question will have to be based on this, the cost associated with a type 1 or type 2 errors. Okay? All right. So are we good in exercise 1032? All right, good. Oops, no. Okay, let's look at this one. And for this, we're just going to use the template. No hand computation at this point. Rudder Nursery Company packages its pine bark mulch in 50-pound bags. From a long history, the production department reports that the distribution of the bag weights follows the normal distribution, and the standard deviation of this process is 3 pounds per bag. At the end of each day, Jeff Rudder, the production manager, weighs 10 bags and computes the mean weights of the sample. And then so, you know, today's production, here are the weights of the 10 bags that Jeff sampled. We will define X, the variable of interest, the, what is this, amount of bark mulch in each bag. Okay, and the amount is measured in terms of pounds. X is continuous. What is the population parameter being tested? It is the true mean fill content of the bags. So we're talking about mu. How do we set up the hypotheses? Okay, so we know that we're going to be testing the mean. Are we going to use this pair, or this pair?
What's our question in this?
I'm sorry?
What's the question in this? It gives the problem.
Oh, yeah, thank you. Is the filling process okay?
So in that case, you're essentially asking us for a two-tailed test because you're just asking, like, is it different?
Is it what?
Well, by asking is the filling process okay, you're just asking us if there's a difference, whether it's positive or negative, which makes it a two-tailed.
Right. So you're saying, Iridian, this one?
Yes.
Okay. So H sub 0, mu equal to 50. Translation, process is okay. All right. It's filling at the target average. H1, mean is not equal to 50. Process is not okay. Why not okay? Well, if the mean is less than 50, that means that they are underfilling the bags. Not good for the customer. If the mean is greater than 50, the process is not okay. It's overfilling the bags. It's not good for the producer, right? Not good for Jeff. So they want to ensure that the average fill weight is exactly equal to 50. So this is a two-tailed test. What is the appropriate test distribution to conduct this test?
It would be a z-test.
The z-test. Why the z-test?
Well, first you said it was normally distributed, which
That's one. More than that, you know, here they have to assume normal distribution because the sample size is less than 30. But there's another information that is provided in the problem.
we're also
that
given the standard deviation.
population standard deviation is known. Okay, so this requires the z distribution.
I did have one more question though. The original question doesn't propose a significance level, so once we, know what we have to know.
Well, we can look at the p-value later on and see if how big it is or how small it is. All right. So even if the significance level is not given at this point, we can just always look at the p-value. All right, so to use the template, we will need to compute the average, the x bar, and the x bar is 48.2. Let's see if that is exactly equal to that number. All right, it's 48.21. Okay. What was sigma? Sigma was given as 3 pounds. And then x bar we computed to be 48.21. So we're still using the z-test. 50 is the hypothesized weight. Direction of test, 1. Sample mean, 48.21, is that correct? The standard deviation is 3 pounds. Sample size is 10. And we can leave this significance level over here. Here, look at your p-value. So here are different scenarios. At alpha equal to 0.1, what is your conclusion? At alpha equal to 0.01, 0.05, what's your conclusion? And at alpha 0.01, what is your conclusion? So is null hypothesis rejected?
I would say yes, because the computed value is in the fail zone of the distribution.
Which one? The computed value? Which are you looking at?
The negative.
Don't look at the the computed value. Just look at the p-value.
So then you would reject.
Huh?
You would reject it, right?
Okay.
Because it's 0.10, right? And then the p-value is 0.05.
All right. So the first one, yes, you will reject HO at alpha of 0 or 0.1. But how about alpha if the alpha were set at 0.5?
You accept it, or
Okay.
fail
Fail to
it. Sorry.
reject, And then at 0.1, also fail to reject. Okay. So if you set your alpha, if Jeff sets it at 0.1, he will reject the null hypothesis and conclude that the bags are being underfilled when in fact, in fact they may not be being underfilled. So that would be the definition of this 0.1 alpha. So are we clear here in this problem? All right, now I have a question though. What is the type 1 error, the interpretation of type 1? What is the interpretation of type 2? So this is the probability, I will start, of concluding filling process, all right? Supply the remaining part of this statement.
So type 1 would be the probability of concluding the filling process isn't okay, even though it is okay.
Okay, isn't okay when in fact it is. Good. How about type 2?
Saying the filling process is okay when it's actually not.
Mm-hmm. Good. All right, any questions on exercise 1030? Good.
I have a question. When do you compare the z and critical value, and then when do you compare the p-value? Or at what?
It doesn't matter. I mean, you can use either one. The problem with using the critical value as a decision rule like this is that you'd have to, in some applications, some applications will not give you the critical value, so you'll have to look it up yourself. But almost all statistical applications will give you the p-value. So it's more for maybe convenience. Using the p-value is convenient because you can just simply look at the p-value and make a conclusion right away. All right. Another advantage of using the p-value as your decision rule is that it can give you an indication of the strength of the evidence that you have. All right. And what do we mean by strength of evidence? Well, let's go back here. You know, when you have a p-value that for that filling example, the p-value was 0.05, a little bit over 0.05. So you can say that the evidence that you have in rejecting the null hypothesis is somewhere between strong and some evidence. Does that make sense, Shoshana?
Yes, thank you.
Okay, you're welcome.
Professor,
Okay.
real quick on that problem, how do you determine that it's a two-tail test as opposed to a left or right tail?
Oh yeah, well, the filling way it has something to do with the that this is a filling process, and as I was explaining earlier, that if the mean is not equal to 50, and if the mean is less than 50, then it's underfilling the bags. If the mean is greater than 50, it's also not a good thing because that means that the bags are being overfilled, right? So for the process to be considered okay, it has to fill exactly at the stated fill weight of 50 pounds.
Oh, I see. Okay, so basically it either has an average of 50 or it doesn't, hence it's two.
Exactly.
Okay.
Okay,
Thank you.
you're welcome. All right, so let's move on. Next problem. According to a study by the American Pet Food Dealers Association, 63% of U.S. households own pets. A report is being prepared for an editorial in the San Francisco Chronicle. As part of the editorial, a random sample of 300 households showed 210 own pets. The question is, does this data, meaning the data that was obtained from San Francisco, disagree with the Pet Food Dealers Association data? And you are to use a 0.05 significance level. Okay, so let's define X first. What is X here? Well, X is the number of households in N equal to 300 who own pets, right? And X is discrete. So from the sample size of 300, what's the value of X? How many households in the 300 households that were surveyed own pets?
210.
210. All right, good. So in this case, the population parameter that is being tested is the population proportion. Okay, meaning we can convert 200 as a proportion of 300. So we compute what is called as a sample proportion, right? Equals 210 divided by 300. So the 0.7 is the sample proportion. How do we set up the hypotheses? Okay, so we know that we're testing a population proportion. The keywords here, or the keyword, is this, disagree. Okay, how does this translate in terms of the proportion? And the American Pet Food Dealers Association said 63% of U.S. household own pets. So 0.63. What's the missing symbol between pi and 6.63? Using this word here.
Not equal to.
Okay, not equal to. Thank you. So this is a two-tailed test. H sub 0, pi equal to 0.63. H1, pi equal to 0, not equal to 0.63. So the translation of H1, this one, the translation is that the distribution of household pet ownership in San Francisco does not agree, or we can say is different from, the U.S. Distribution. Okay, does that make sense? All right, so the HO here would say the distribution of household pet ownership in San Francisco area agrees with, does not. Okay, so that is the interpretation of the null hypothesis. What is the appropriate test statistic for carrying out the test? Well, let's go back to the flow chart. We're doing a population proportion, and then the sample is large enough such that this condition is satisfied. So the appropriate test would be using the Z distribution. Okay, so over here. So the Z distribution as an approximation to the binomial. Okay, so let's solve this problem using the template. Okay, we will be using test involving the proportion. Select this option. The hypothesized proportion is 0.63, as stated in the problem. The direction of test is, it's a two-tailed test, right? Set it up as equal to, not equal to. Sample proportion, we will compute that as 210 divided by 300. Sample size, 300. Significance level, I think it's 0.05. So here's the output. So based on this output, render a conclusion on the null hypothesis. Okay? Complete this line. At the 0.05 significance level, the null hypothesis will be rejected or not?
Rejected.
Okay. Okay. Why did we say rejected? The null hypothesis will be rejected.
Well, I rejected it because the p-value was less than the alpha, but you can also see that the test statistic is past the critical.
Right. So you have to you have two numbers to cite there. First of all, the p-value is less than alpha. The alpha was stated as 0.5. Secondly, you'll see that the computed value is inside the reject HO region. So either one should give you the same conclusion. So that is the statistical conclusion. What is the answer to the question that was posed here? Does the data disagree with the Pet Food Dealers Association? So does the data, meaning the San Francisco data, disagrees with the Pet Food Dealers Association data? What's our answer? Yes or no? Meaning, what is the interpretation when we conclude to reject the null hypothesis?
Can I look at the original question?
Yeah, so over here, I'll just retype the question here. Does the San Francisco data disagree with the Pet Food Dealers Association data?
Then yes, it does.
Yes, it does. Correct. Okay. Another question. How strong is the evidence, sample data, in support of rejecting the null hypothesis? Give me a descriptor. You refer back to that sheet where you have that
I
slide.
believe it should be strong.
What was that, Iridian?
I think the evidence should just be strong since it is it's greater than the 0.01. I think if it was 0.01 or under, it would have been very strong.
Yep. It's probably more than, it's probably, so it's somewhere between very strong and strong, right? Because
Yeah, it's just
the value is 0.012. So we can say that maybe very strong by virtue of the p-value.
Professor, I couldn't find that page on the template.
Did you download the one that I saved last time we met? It should be there. If not, it's in this one is in your PowerPoint.
Oh, okay.
Okay. Now, maybe after today's session, you can, because this is automatically updating the file that is linked in Moodle. Okay. Okay. Suppose that you run a pet store in San Francisco area, and you're interested in knowing, the percentage of households in the San Francisco area own pets. So this is a kind of question that you might be interested in answering. Where will I get the answer to this question?
It's right on the page. It would be 75.19%.
All right. Well, that's just a point estimate. So you are citing. Which one are you using, Iridian?
Oh, I was just using the upper confidence limit, but technically.
Okay, so you're using that number, correct. So you will be saying that the true proportion of households in the San Francisco area, the very worst is probably around 64.8%, or best case is about 75.2%. Okay, and these numbers are that. So you will say that you are 95% confident that the interval 64.8% and 75.2% contain the true proportion of households in the San Francisco area who own pets. All right, if there are no questions, then we'll move on to the next and last problem. After losing a season, or after a losing season, there is a great uproar to fire the head football coach. In a random sample of 200 college alumni, so we say N is equal to 200, 80 favor keeping the coach. So of those 200, 80 are in favor of hiring the coach. So we can define X here as the number of college alums in the sample of 200 who are in favor of keeping the coach. And X is discrete, okay? What is the population being tested? Don't have to think much for this problem because it's actually stated in the problem. Okay, so the proportion of alumni who support the coach is less than 50%. So translated, pi less than 0.5. So here, we're talking about the population proportion, pi. And then how do we set up the hypothesis? We already converted the statement into here. So that would be the alternate hypothesis, pi less than 0.5, h1, h sub 0, pi is at least 0.5. Alpha is 0.05. So since we have x out of n, 80 divided by 200, this produces a sample proportion of 0.4. Okay, so this is P, or sample proportion. What is the appropriate test statistic for carrying this test? Again, this will be the Z distribution as an approximation to the binomial. All right, so let's use the template. Still using this same test for one population proportion, Z test. The hypothesized proportion is 0.5. And this is a less than test. So the direction would be left-tailed. Put 3 here. Okay, so we note that this is consistent with how we wrote the hypotheses. Sample proportion equals 80 divided by 200. The sample size is 200. Significance level of 0.5. All right, so that's the output. Now let me copy the same things here. So what's our conclusion? At the 0.05 significance level, the null hypothesis will be rejected or not. Again, just look at the p-value.
It's going to be rejected.
Okay, so the p-value is 0.023. It's less than the significance level. Okay, what was the question? Okay, is the proportion of alums, or is it the true proportion of alums who support the coach less than 0.5? Yes or no?
Yes, it is.
Okay, because we rejected the null hypothesis. And by rejecting the null hypothesis, we are saying this. The proportion is less than 0.5. Third question. How strong is the evidence in support of rejecting the null hypothesis?
Very strong.
Very strong. In fact, probably, is there a word there, extremely strong?
It's close, but it's away from at least 0.013.
So almost extremely strong, right? Okay, so what is the true proportion of alums who support the coach using the 95% confidence level? That would be this, right? So it's somewhere between 0.3321 and 0.4679. Or in terms of percentages, it's between 33.2 and 46.8%.